I will start this webinar talking about a short introduction and motivation. So welcome everyone. I hope you can hear me right now. So we will begin our webinar with a short overview in this picture. And as you can see right here, we have reliability methods all along or for every stage of the product development process. And I think it's quite clear to ensure the development of high quality products, we have to address reliability at every stage or all along the product life cycle. So not even the product development process, it's the whole life cycle, as you can see here in the operation and recycling. So starting with the reliability planning, we have to set up targets. Then the next step is always, let's say qualitative analysis, like to get an information about the critical failure modes or failure mechanisms. And then, this is our special focus in this webinar, the so-called reliability demonstration. So at the end of the product development process, so in our design stage, for example, we have to make sure that our product meets the requirements. And this is what we do in reliability demonstration. Most of the time we are using reliability tests for this demonstration. And as you might know, life is not a deterministic variable. It's stochastic in nature. So test planning is not that easy. And this is the main motivation for today's webinar. So, the last steps for sure to get it complete is reliability assurance in production and reliability prediction for field use. But our focus, as I already said, will be the reliability testing and demonstration. So the key issue of efficient test planning is always that we want to have, let's say, most suitable test strategy for our individual case, or meaning for our individual product or process. So the first decision is always between to choose either the test to failures or so-called end-of-life testing. This means we are forcing failures, so we test every unit or a certain amount of units or specimen till they fail. The other option is the so-called, in Germany we call it success run testing. I think in the English-speaking countries it's more like zero failure testing. So no failures at all. We want to test to a certain lifetime and then make a reliability demonstration. So, and I think, the most of you guys want to have a test strategy with minimal effort, I think. So meaning a minimal number of specimens, for example, minimum required testing time, and also minimum of costs, I think. Before we get deeper into the whole test planning procedure, we will shortly address the main difference between the so-called the success run testing and the end-of-life testing. A common pitfall is to think that success run testing is necessary when it comes to reliability demonstration, but it is not. So you can also use an end-of-life based test strategy to do your successful demonstration. But as you can see on top of that, you can use end-of-life tests also in this part when it comes to weakness analysis and reliability assessment, because only in end-of-life based test strategies we are able to estimate our viable distribution for our failure behavior, to make a statement about the maybe of scattering or the scale of the failure behavior. So success run is still can only be used for reliability demonstration, but it's not necessary. So then we can make a further step deeper into detail. So what's now the actual problem when it comes to reliability test planning? So we are starting with the success run test planning. So we will use the same example all the time. For example, 10% failure probability or 90% confidence. 90% reliability and 95% confidence. So as I already said, in the success run, we are testing all our units to a certain point in time. In this example, it is 10,000 life cycles. And we hope for that none of the units is going to fail. So when we have no failures at all, we cannot estimate a viable distribution as it is here shown with the dashed lines. So the question is now, how can a demonstration still be made? And yeah, the solution, the only solution for this kind of problem when we have, let's say, too little information is the worst case assumption. And this is actually success run testing. Success run is a worst case assumption. What do we do in success run testing? So the requirement is 10%, a maximum of 10% failure probability. So what we're going to do is to look for that sample size where the failure probability of the first failure is just a little bit under our requirement. So here I got for you the table for the binomial confidence bounds. And as you can see, for exactly 29 samples, the failure probability for the first failure is just a little bit under 10%, so 9.8%. So as you can see, it is a totally worst case assumption because due to the lack of information of the failure times, we have no other chance when it comes to this kind of testing scenario. So absolute worst case assumption. So this is the more mathematical background of the success run testing. I think most of you guys will know the approach which is shown here. It's a so-called binomial distribution or binomial approach. So this is exactly the same as I showed you before, but is the mathematical formulation of the success run testing. So this is actually the quite easy test planning method. As you can see, yeah, we are inserting confidence. We can insert our reliability goal and then solve for n, and then we get the necessary sample size. But when we take a closer look at this equation, what does it say? We have a 1 minus reliability. And when you think about that, that's actually a failure probability. And this is also the basic idea of success run testing, as I showed you before, because when there is a certain reliability for all the tested samples, which is r to the power of n, and then we calculate the failure probability of this, let's say, system for our tested samples, and none of the samples is going to fail, then we can use this probability for our confidence for the test. So this is actually the main idea also for the success run, as I showed you in the slide before. But did you ever thought of what this is what's the meaning of this for your actual success run test? And this is shown on the next slide. So just imagine we are sticking to the same example in this slide as well. So 90% reliability and 95% confidence. So we have to test 29 samples, and as it is shown 2 slides before. So we have to test 29 samples to this 10,000 life cycles. So just imagine our real failure behavior. We will never know it with a success run test, but just imagine that the dashed line is the real failure behavior of your product. So that means that every sample we are going to test until the 10,000 life cycles has a failure probability of exactly in this example 3%. So 29 samples with 3% failure probability is resulting in a, let's say, system reliability of only 41%. So in this scenario, the probability of not observing any failure would just be about 40%. And I think, this is an extremely bad chance of success. So in this worst case scenario, you will never be able to get a successful result in your test because the chances are very low. The only way out of this is to lower your requirements, as it is shown right here. So when our requirement is not 10,000 life cycles, is 1,000 life cycles, then I think the change is quite clear. We only have to test our 29 samples to this 1,000 life cycles, and the failure probability is decreasing to 0.2%. 2% for every sample, resulting in now a system reliability of 95% for the whole test. So yeah, this means in this scenario, the chance of success or of a successful reliability demonstration is quite high. But yeah, on the other way around, this means that we need more oversizing for successful success run testing. So I think this is not only also not quite good for you in product development. Okay, let's sum this one up. On the positive side, we can say success run is very simple test planning. Yeah, but only on the first look, let's say it in this way. And on the other hand, we need frequently high sample sizes, especially when it comes to high requirements. And we can also make no statement about the actual failure behavior. So we get only the information of the minimum reliability as I showed you in the slides before. So what is needed the most? We need to quantify our chance of success, that we don't have a test that cannot fulfill a successful reliability demonstration, as it was, for example, with the 40% in my example. So now we talked about success run testing, but what about end-of-life based testing? So the main difference when it comes to end-of-life based testing is that for this test strategies, we don't even have an analytical way to solve our test planning problem. So yeah, this is makes the challenge even bigger in my opinion. So what can we do when it comes to end-of-life based test planning? So we go exactly for a sample size like in success run test planning, but we destroy all our products. How many? I think it should be 10 or something like this, 10 samples, destroy 10 samples. Yeah, and I think then the next steps are quite clear. We use the samples we destroyed in the test planning to estimate our viable straight or viable distribution. In this case, yeah, most of the times we use the viable distribution, but you can also use log normal distribution, for example. And then, yeah, we have to estimate our upper confidence limit, because we have to make sure that our statement is also valid for the population and not only for the sample. So, and then when we know our requirement, yeah, we can compare the requirement to our demonstrated lifetime, it is in the blue X right here. Yeah, and in this case, this would be a successful test because our demonstrated lifetime is higher than my requirement. So the problem right here is now, when it comes to test planning, we want to know before how good a chosen test strategy is going to be. So just imagine we go for a second run with this scenario. So due to the stochastic lifetime in nature, we will get a slightly different result. So not the same lifetimes as it was in the first run, we will get slightly different results. So in the next steps, first of all, yeah, for sure, the requirement stays still the same, but the next steps, the viable distribution will also, or can also change a little bit, and also the estimation for the upper confidence limit. So in this case, only due to the natural scattering of the lifetime, maybe this can look like this, for example. So in this case, our requirement is bigger than the demonstrated lifetime, and in this case, it is not a successful run. So in summary, end-of-life tests, I think this is quite clear. Specimens are tested until failure. But we get an information about the actual failure behavior because we can estimate our failure distribution. And as you can see, the problem is actually the same. We need a quantification of the chance of success. So the problem is the same for end-of-life based testing or for zero failure based testing. So, and this is now where Alex takes over when it comes to how we can quantify this chance of success.
Okay, so thank you, Martin. So like Martin said, the challenge here is to find a method to quantify the chance of success to be able to actually demonstrate the required reliability. And we're going to do it by the measurement named probability of test success. You already know by the title of this webinar, of course. The probability of test success is exactly what we want. It's the probability of our reliability tests to succeed in demonstrating the reliability requirement, considering individual boundary conditions. Of course, there are multiple boundary conditions, first and foremost being a time constraint and, of course, a budget constraint. For example, the different sample sizes result in different costs of the test, of course. So how do we formulate our probability of test success? Martin showed you that the demonstrated lifetime with confidence does scatter during a end-of-life test, for example. And the output of the test is what we want. We want to have a greater demonstrated life test than the requirement. So the probability of test success is actually the probability of what we want, a greater demonstrated lifetime than the lifetime requirement. So like we've seen this scattering of the demonstrated lifetime of an end-of-life test. If we imagine doing a multiple tests of an end-of-life test, we could get a histogram like that of the demonstrated lifetimes. And of course, we can find some distribution describing this scattering. And if we now have a look at our required lifetime of the product, of course, some of the demonstrated lifetimes of the test will fall to the left of our requirement, and some, hopefully most of them, will fall to the right. And if we take the area in blue here, under this distribution, it's the probability of test success. It can be formulated via a integral. You can see it here, but we actually don't really have to calculate it in any analytical form, but more about that later. So the main key points here are, if we have a prior knowledge about the failure mechanisms or the failure distribution of the product, and the scattering of the demonstrated life can be calculated, and therefore the probability of test success can be calculated. Our approach is relatively easy in its basic form. We make use of a Monte Carlo simulation using the prior knowledge about the failure distribution in form of a Weibull distribution with shape parameter B and the characteristic life T. And this integral can then easily be solved by simply counting the demonstrated lifetimes being greater or equal to the required lifetime and divided by the total number of Monte Carlo iterations. So like Martin already mentioned, for a success run, the chance of success, so the probability of test success, can easily be calculated by the binomial approach. And the example Martin showed you, it was about 41% chance of success. If we take the failures into account, F or I, in this equation, the binomial equation, as you already know it, probably gets a little more complicated, but it's still very simple to calculate in an analytical form. If we take an even broader view about this measurement, we can interpret our probability of test success as the power of the physical reliability test being the complement to the beta error of type 2, and the confidence being then the complement to the alpha error of type 1 in a hypothesis testing framework. So by calculating the probability of test success, we can know before doing tests how successful these tests or the different test configurations can be and will be, and are then able to assess those tests in a manner which is very suitable for reliability test planning. So I now give way to Thomas.
Hi, everybody. So now we've heard a little bit about the theory and the basics of this concept, and I want to tell you something about the application of the concept. So, because this is relevant for us. We have here a typical initial situation that you probably all know. We have a reliability goal, which is reliability R, typically 90%, sometimes also 50%. Then we have the confidence, which is also chosen as 90% or 95% here. And then we need the prior knowledge. Alex already told you about this prior knowledge. In our studies, we use the Weibull distribution T and B. Some of you know it as eta and beta. So yeah, where do we get this prior knowledge? That's the first part of the test. In success run testing, we need to make an assumption on the beta or the shape parameter of the Weibull distribution. But for our test planning here, we need to make an estimation of this prior knowledge and need some idea of where our results will be or could be. Then we have a lifetime requirement that we want to demonstrate, which you get from your system reliability or lifetime requirements and your component requirements. And then we have a cost and a time budget that we want to consider. Here I show you the extended probability of test success approach that I'm gonna introduce to you. We have this preliminary information, which is pretty much the prior knowledge. So we go into our approach with the Weibull distribution of our component. Then we select the test type and the test configuration, which might be an end-of-life test, could be an accelerated end-of-life test or a success run test. We perform some simulation by generating failure times repeatedly. Then we perform a maximum likelihood estimation to estimate our failure behavior and the live model parameters. And then we do we keep going on with our classic Weibull analysis to determine the confidence and then the lifetime that we can demonstrate within this simulation step. Then we repeat the simulation step a lot of times, and then we can determine our probability of test success considering our reliability target. What's new in this extended approach is the much bigger variety of test strategies, because the accelerated tests, of course, are highly relevant for application, and also the lifetime model parameters, because we needed this step for the accelerated tests. Here at Institute of Machine Components, we implemented all these ideas that we presented to you in a tool called Optima. This stands for Reliability, Optimal Planning of Tests at EMA. EMA is the institute's name. And here you see the GUI of this tool. I'm gonna introduce you this one micro tool. It's called Optimum. It enables the analysis of the parameters that you enter here. We first have the strategy types. Here it's the accelerated tests with 2 load levels. Then we determine the number of specimens that we want to consider, which represents the parameter space, the load levels, and then here there's the prior knowledge, so the Weibull distribution, the reliability goal, the lifetime model, and some further boundary conditions like a cost model and the budget and stuff. And then here on top we have the Monte Carlo simulations that we want to perform. Then we run the simulation, and what we get is this table as a result. Here we have different optimality goals. The first one is the maximum demonstrated lifetime. So which from all the test configurations that we considered, which one is the best test that demonstrates the best or the highest lifetime. And here we see that we need to 18 specimen on the lower load level, 24 specimen on the higher load level. Here's the load level height, and this is the demonstrated lifetime, which is standardized by the characteristic lifetime. So we can demonstrate this lifetime by this test configuration, and this will be our final cost and our total testing time. Then this tool also gives us the cheapest test, which will be much cheaper, but also fulfills our requirement, which was 0.15 as demonstrated lifetime. And then we also have the shortest test, which is also relevant for product development. If we have not much time and we just need results and to demonstrate it quickly, then we use this last test. What you can see, this one is the shortest test, especially since most of the specimen are on higher load level. So 30 of the 33 specimen in total are on the high load level, which means a short high acceleration and a short testing time. But of course, our demonstrated lifetime decreases. So with this tool, we can simulate pretty much all relevant test configurations that we are interested in. And now there's the question, what other possibilities do we have with this tool, with the other micro tools, and with the full approach of the probability of test success? I already talked about the accelerated test, which is highly relevant for industries since we need this acceleration. We cannot demonstrate 7 or 10 years in field without accelerating our test, so we can highly reduce our testing time. We have this extended PTS approach for that. And then we have other ongoing studies that we are working on. One, for example, is the demonstrated lifetime. So how can we the demonstrated lifetime versus the number of specimen on each load level? So here we have the question, how do we split our specimen on lower and higher load level to achieve the best demonstrated lifetime and to get the most efficient test strategy for our application? Then we want to investigate censoring strategies. Of course, if you have failures and you have survivors in your test, you need to analyze them with censoring, considering censoring. But is it relevant for test planning? We want to investigate this. And then we also have the issue that sometimes we have multiple failure mechanisms, or we have more complicated systems containing several components. And of course, we want to have a test strategy that considers all components, all failure mechanisms, and gives us the best and the most efficient test strategy. Here's the basis of the accelerated test, how this works in the approach. First of all, we generate virtual failure times at the lower accelerated load level, which is shown here. Then we do the same at the higher accelerated load level. That's why we need the prior information, the viable information, and the lifetime model information. Then we do some maximum likelihood estimation to estimate the characteristic lifetimes on both load levels and the viable shape parameter. We do some interpolation here and can also extrapolate this on nominal load. And then we know the characteristic lifetime on nominal load. So this is the one plot where we investigated the demonstrated lifetime versus the ratio of specimen on lower load level. So here you see how many of the number of the samples are on lower load level. If we are 50%, then 50% are on lower and 50% are on higher load level. And as you can see, we shown that plot for several total number of specimen. And as you can see, the more specimen we have on lower load level, the higher the demonstrated lifetime gets, until we reach a maximum, and then it decreases again. So the best test configuration for 50 specimen in total would be somewhere like here, right? 70% at lower load level and 30% on higher load level. This would be the optimum, but if we talk about efficiency, then we also might choose this strategy, which is more like 55% on lower load level. That means that we shift some of the specimen from lower to higher load level. That means a higher reduction of failure of testing time and a higher reduction of testing cost. And this is what we can do with this tool and with this probability of test success approach. Besides from maximizing our demonstrated lifetime, we can also look at other optimization goals. So maximization of the demonstrated lifetime, I've shown you this. Then minimization of total cost or time was, for example, the idea of shifting specimen to a higher load level without reducing the demonstrated lifetime much. And also we can use this approach to determine the exact failure behavior. So this means to determine the best test configuration for parameterizing our viable distribution. And we can do the same with the lifetime model parameters. So we know, for example, we have a Wöhler model and we want to know the Wöhler parameters. Then we use this approach, perform a different optimality analysis and get the test that gives us the best lifetime model parameters. Here is a comparison of a couple test configurations, which is quite interesting, I think. We have different test types that are entered in this plot. We have the test cost for a certain cost model. Of course, this is logarithmic. And then we have oversizing on the bottom axis. Oversizing is in terms of lifetime. So 100% oversizing means we doubled the lifetime. So we have a requirement and a component that is 50% oversized overfulfills this requirement by 50%. And as we can see, the success run test is only entered here at 70 to 90%. So this tells us the success run test is the cheapest. We can see that for components that have high oversizing. My colleagues already said that success run test has a low probability of test success for in most cases, unless we oversize far or much, and then it has a good probability of test success. But of course, we don't want to have this oversizing here. And if we make our oversizing smaller, we see that the accelerated live test is the cheapest in these areas, the violet one. This accelerated live test also works for oversizing from 30% on or bigger. So this is a quite good, well-designed product. If you want to come even closer to the edge of in terms of oversizing, then we need to talk about non-accelerated tests. Yeah. So this plot pretty much shows what we want to tell you. If we have high oversizing, then the success run test can be successful and the cheapest one. If we have low oversizing, then we need to switch to the accelerated test because the success run test cannot fulfill the requirements anymore. And then we have an application example from a brake caliper. You all know this from your cars. We have some input data like the shape parameter, the characteristic lifetime. We have some cost parameters for the cost model. And here are the requirements for the test. This is a pretty high requirement, 94%, but of course it's a safety relevant component. And what we want to show is this 16,000 life cycles. We plug it or we enter it into our Optima tool and find the optimal test strategies for all test types that we considered. And what we can see is that the best test strategy is, of course, the accelerated test. We can achieve the probability of test success that we wanted to have. We have a sample size of 27 and a cost which is compared to the others one of the lower costs. Also the same with the test time that we get. If we look at the end of life test strategies, we see that we either have the requirements fulfilled, but then higher cost and higher time, such as the non-sensor test. For the type 2 sensoring test, we cannot fulfill the reliability requirement. So this is cheaper and shorter, but it doesn't fulfill the requirement. And then we have the success run tests, and we see that we have higher cost, much lower time, but we cannot fulfill the requirement at all with the success run test. And even if we consider one allowed failure during the zero failure test, we can increase the probability of test success, but not achieve the requirement. Yeah, that's it from our side. We are the Martin Datzer, Alexander Grundler, and Thomas Herzig. That's me. We are all head and members of the Institute of Machine Components and the Department of Reliability Engineering. And yeah, I'd be happy if you have any questions. Please use the Q&A chat function and yeah, let us know. Thank you.
Thank you.